Good morning, everyone. I'm Shurok Khozam. I would like to present my thesis that I defended last May, supervised by Grégory Plan, Sébastien Texey, and Eric Totel, as a part of Griffin project funded by ANR. My thesis is AI-based response and programmability of future networks. I will start by motivating our problem. Then I will cover the related work approaches and its limitations which shaped our research objectives. I will concentrate on the third approach that I have proposed in this thesis. Then I highlight our key contributions. I will close by limitations and future work. Why mitigating DDoS attacks matters? These types of volumetric attacks are rising in functionality as well as in scale. And according to Cloudflare report, there's a 500% increase in network layer attacks over a year, and more than 123% rise in application layer attacks. These are not just statistics, also many botnets and DDoS attacks are escalating in size from 1.3 terabit per second in 2016 to around 15 terabit per second in 2025. And the main cause of this surge is the proliferation of IoT devices, which made it easier for attackers to exploit these devices and to launch large-scale type of decentralized attacks that make it difficult to simply block the source of the attack. This escalating trend highlights for the research that I'm presenting today. Yeah. Before presenting my project, I will just cover what we have already in the related work. We have traditional approaches like rule-based methods, routing, signature-based, and other approaches, which while these approaches were efficient historically, so they want to try to see. You can move it. Right. Yeah, I would need the devices. You can basically try to stop it. Yeah, so no, I think no. Oh. Un, deux, trois. Yeah, with your hand. Okay. While traditional-based approaches were efficient historically, but they were simple and fast, they provide low computational overhead, but they lack adaptability to changes in network conditions. They need the automated rule update or adaptive threshold tuning. They often provide latency, which is unsuitable for real-time applications. Then the field moved toward machine learning approaches like support vector machine, random forest, and others. But these approaches mainly focused on detection without providing a way of how to mitigate these attacks. And they mainly focused on small attack coverage. Then the other approaches, like deep learning approaches, tried to address these gaps by providing deep learning approaches. It's not what. Yeah, it's just a disconnection. It's not. I can use the box maybe. It's
I tried to change the.
Yeah. Yeah. Then the field moved toward deep learning approaches that they try to provide automated countermeasures for attack mitigation, but they mainly share several limitations. The most important one is lack of scalability, and they mainly ignore the quality of service preservation for legitimate users. So our objective is to design adaptive DDoS mitigation system in software-defined networking, and we want to provide adaptive countermeasure selection to dynamically adjust mitigation strategies based on real-time network conditions. We want our system to be scalable and remain effective as network size and topology evolve over time. We want to preserve quality of service while mitigating the attacks. Also minimize the computational and the resource consumption for real-time deployment. I want our system to be resilient across the different types of attack scenarios. So to address these objectives, first we adopt deep reinforcement learning mechanism, which at its core we have an agent that takes an action in an environment. Then this action would be rewarded with a negative or positive reward according to its effect in the environment, if it's aligned with our predefined objectives or not. And all these observations will be stored in a replay memory to be replayed during training iterations till we reach our predefined objectives. I will highlight on our in this presentation on our third approach. Our third approach is called SMART for scalable permutation-aware design. So first, this is the system architecture that we have proposed. So it's composed of 3 planes. We have data plane where we have our SDN network composed of entry points and switches. We have an attacker. Then we have a monitoring system represented by Shurok, which capture packets on switches interfaces. We focus on the white area, which is the provider network, and then we have a CIC flow meter, which extract the raw data provided by Shurok into CSV file, and we would capture now all performance and traffic metrics. Then we have a customized controller in the control plane that it would send all these metrics to the application plane to form the state of the neural network, would be used as an input. Then we have our RL model that it's trained using DDQN algorithm, double DBQ learning algorithm, that it would provide automated countermeasures to be applied on the switches interfaces and for mitigating attack and preserving quality of service. The controller would transform the actions provided by the RL model from high level to OVS, Open Virtual Switch rules, to be applied on the switch interfaces. Now, for state representations, so we focus on traffic and performance metrics like total packets, received and transmitted bytes, and performance metrics like jitter, latency, throughput, and others. And all these metrics are collected on switches interfaces. In the reward function, our main goal is to preserve network performance for legitimate users, and we mainly focus on latency and jitter, while ensuring efficient resource consumption. We provide in the reward equation, first, we use the weighted averaging to reduce sensitivity to short-time fluctuations and to promote stable learning. So we use weighted averaging for X, which is the performance metrics, latency or jitter, throughout iterations. Then we calculate the delta for this metric over all the training iteration to see if the performance is increasing or decreasing. Then we use logarithmic scaling for the delta to encourage incremental gains and prevent extreme reward spikes. We penalize the agent for excessive bandwidth increase without and for excessive path length also. The final reward would be by subtracting the resource penalty from the reward for the X jitter or latency, jitter and latency reward. And we have a set of termination conditions for reaching worst case or best case scenarios, and for avoiding stagnation in reward in the RL model functionality while taking repeated do nothing actions. We propose in this approach a mechanism called the state projection mechanism for decreasing input dimensionality of the input of the neural network, which has the effect on the minimizing the cost of resources, which we will see that in the results. But this mechanism, what we do is that we group entry points by their controlled switches, and then we calculate, instead of providing the state for each entry point to the RL agent, we provide the state of a group of entry points. So for each group, we calculate for aggregation functions, mean, max, mean, and STD, standard deviation, for each metric over all the entry points in a group. And we use for training the RL agent algorithm a modular decision-making architecture. It's dynamic neural networks. We have different models. First, the G model, which is responsible for providing redirection actions of a group. So we have as input the state metrics for the group of entry points and for the control switches. And as an output, we have our countermeasures, which is either redirection actions or do nothing, as we have in the DN model, do nothing actions, and as we have in the S model, switch model. It's controlling bandwidth actions to control bandwidths between control switches and control switches and the centralized switch. And the global model would be constructed by concatenating all the inputs and the outputs, and then the agent would select the action corresponding to the highest Q value using argmax operation. And this is our experimental setup. We have different entry points. Each entry is a whole subnetwork composed of control switches and entry points. We emulated this experiment on using MiniNet. And we run the experiment on a dedicated server. We tested till 100 entry point. And we also tested on network and application layer attacks. And this is an example of the results that we got. So here we compared our three methodologies, first without projection, with projection mechanism, without projection mechanism, and with the QoS-centric approach, which is our second approach. So in the x-axis, we have the iteration steps, and in the y-axis, we have the value of the performance metric. Here we have latency and jitter. So we can see how performance is degrading without countermeasures, and we got the best results for with projection mechanism. And overall, and this is evaluated under network layer attacks. And we got around 50% reduction in network layer attacks, around 68% in application layer attacks, 88% in increase in throughput under network layer attacks, and more than 200% of throughput under application layer attacks. We tested till 100 entry points the jitter. So under application and network layer attacks, and we found that jitter stays less than 0.19 second till 75 entry point, and still less than 0.25 at 100 entry point. And we evaluate our mechanism that we proposed, which is state projection mechanism, to see its effect on the number of neurons. So we have on the x-axis number of switches with a valid number of entry points, and on the y-axis we have total number of neurons. So we see that at a small first, compared to our second approach, we got around 65% reduction of number of neurons using with projection mechanism. And I want just to say that at a small scale small network scale, we do not see the benefit of using this mechanism, but we start to see it when the number of at large scale networks, for example, when controlled switches greater than 18 and entry points greater than 200. So as a recap, this is all the approaches that we have proposed during the thesis. We started by focusing on small network size, providing only one type of countermeasures. Then we moved to another approach. We extended our network. We covered, we used dual actions. Then in the smart approach, we focused on ensuring at first place the scalability of these approaches. And we have a publication and GitHub link for each of these approaches. I will present it later. But the main limitations that we have is that now we are focusing only on volumetric attacks. We didn't test on slow rate DDoS attacks, for example. The scalability is in terms of number of entry points, but we didn't scale in terms of number of controlled switches. And what it could be good to be done is to test on larger and heterogeneous topologies. Maybe using also other types of algorithms, as we are using now double DB calling algorithm, which is used for discrete actions. So we can explore continuous actions with algorithms like proximal policy optimization or soft actor critic. And this is the list of our publications with the GitHub link. You can take a picture if you want more details. Thank you.
Great. Thank you for your presentation. I just have a very small and quick question in how how you can quickly describe your traffic modelings. Maybe you don't mention about the traffic that you model.
Traffic, yeah.
How do you generate the traffic and how you measure the KPIs network or for all the matrix that you have been mentioned, you are actually run live
Yes.
data traffic, or you have the open source data, or which metric you are actually measured live, or you manually computed or something, right?
Yeah, thank you for your question. So we used varied tools throughout approaches to provide real time traffic. So in the first approach, we used the Scalable, but in the later approaches, we used for generating malicious traffic, an open source tool. It's called MHDDoS, which is available on GitHub, and you can what is good on this tool that you can manipulate the code in order to increase the intensity of the attacks that you are generating. And for generating legitimate traffics, we use the custom-based tools. Also, you can manipulate the codes to increase the intensity as you want. And we thought that it's maybe could be better than rather than using data sets. Yeah.
So I just a quick clarification question. Is this a fully distributed system, or is some of the calculation happening in a centralized place?
It's
Is this a fully distributed system that you're building here, this whole modular kind of thing, or are you bringing all this data to some central location for processing? I was a little bit not clear on how much of this is centralized versus distributed.
no, actually, it's not distributed.
It's not just, so it's all, you're collecting all the data but you aggregate in sort of subsets of, right? You aggregate the data in these subgroups, but everything
yes.
is passed to a central node for processing.
Yes, yeah, actually we consider that we gather all, we can capture all the traffic. But we can capture all the traffic, but we also have aggregation of the traffic that we have using the projection mechanism that we propose.
Right, I see.
Yeah.
Okay. I mean, are you thinking about a more distributed solution in the long run? Just that,
yeah,
you
it's
know,
maybe
try
a
to
good
push
idea.
throttling towards where it's actually happening, so you don't have to send so much data to the back end.
Yeah, I think that it could be a good idea for extending this work.
Yeah.
Yeah,
And
it will be more realistic also.
I'm also just curious because you mentioned that part of the rise in DDoS is happening because of IoT devices. Do you, what's actually happening? Like, are there certain kinds of IoT devices that are being compromised more than other kinds, or?
Yeah, what I wanted to say that IoT devices are, since they are distributed now and they're easily accessible over the internet, and they have low security.
Sure, yeah.
Yeah, so this made it easier for attackers to launch their attacks. That's what I meant when
I see. Okay, but I mean, I'm wondering, like, you know, is it home security cameras, or is it like smart speakers, or, you know, home assistant? What kind of devices?
it could be
It could be any, but
yeah.
is what's actually happening in the real world? Are they Are there actual real DDoS attacks that are occurring because these things are being compromised?
Yeah,
Or is this just
what is
it
needed for
theoretically
an
could?
attacker, DDoS attack, to launch its attack is an equipment that it able to launch its code, malicious code, and that's also, I think that what I meant, it may be mobiles or laptops or maybe cameras also,
Maybe cars?
maybe cars.
Okay, thank you.